Welcome back, everyone. In this series of videos, we're going to look at our unit on two-dimensional motion. So we're talking about motion in 2 and 3D, including the motion of projectiles. So what we're going to be doing is basically looking at how we can represent the motion of a body in 2 or 3D using vectors, and how do we find the vector velocity of that object using knowledge about its path. And then finally, we're going to look at the acceleration of an object moving in 2 or 3D. And we're going to look at a case of where an object can have acceleration even though it has a constant speed. But we're going to first think about how we would set this up if we had a displacement problem in a couple of dimensions. So we move 10 meters north, and then 6 meters east. Then we climb a 3-meter platform and we move 1 meter west on that platform. What is the displacement vector? Okay, so let's break this up and let's just say that we have upwards like this, and we have east going like this and north going like that. Okay, so we can translate this into unit vectors, I hat, j hat, and k hat. And then if we translate these displacements, 10 meters north would basically be 10 meters j hat in the positive j hat direction. 6 meters east would be plus 6 meters I hat. Then climbing a 3-meter platform would basically be plus 3 meters k hat, so in the z direction. And I guess we put the parentheses there. And finally, moving 1 meter west would translate into -1 meters I hat. So if we take all of those and add them together, it looks like our displacement vector would be 5 meters in the I hat direction, 10 meters in the j hat direction, and 3 meters in the k hat direction. So what we say is that this is our displacement vector, and this is made up of 3 components, rx, ry, and rz, which are typically multiplied by the unit vectors. So that's how that looks. And so this is just a more formal way of saying this, that if we want to talk about a unit vector in terms of magnitude and direction, our vector r is rx I hat plus ry j hat plus rz k hat. And the length or the magnitude of r is given by the square root of the sum of the components squared. And so this is an extension of Pythagorean theorem to 3 or more dimensions. So now let's take our sample problem from before. Remember that we had for this that r was equal to 5 I hat plus 10 j hat plus 3 k hat. And we want to find how far we are from our starting point. Well, that's just the magnitude of r. So that's going to be the square root of 5 squared plus 10 squared plus 3 squared, which is the square root of 134, and then that will be in meters. Now, if we wanted to know in what direction, well, we have 2 choices. We can use the unit vectors I, j, k to specify direction, or our alternative is to specify 2 angles. Remember, we talked briefly about this in the prior unit, but if I have a point up here, basically I have an angle along an equator like this, an azimuthal angle, and I have a polar angle. Okay, so I could talk about this in terms of r, theta, and phi. Actually, I think it's in the wrong order. It's r, phi, and then theta. So that's just one way to write the direction. Okay, so now what we can do is take what we've been talking about in one dimension and translate it into 2 or 3 dimensions. So if x is position, delta x is displacement, v is velocity, and a is acceleration, then we can translate that into r being position. And the components of this position vector are x, y, and z. And they are in the I hat, j hat, and k hat directions. Displacement is the same. We will have delta r, which is delta x I hat plus delta y j hat plus delta z k hat. And then velocity and acceleration are similar. Okay. So let's look at a few examples. First, we are given that a position of a particle is given by r equals 80 plus 2i hat minus 40 j hat minus 5t squared k hat. And we want to derive the velocity and acceleration vectors for this particle and talk about what its motion looks like. So one piece of notation that I want to introduce is that instead of saying that we have position, which leads to velocity, which was dx dt, now we have position, which leads to dr dt, which is velocity. Okay, so velocity is now going to have an x, a y, and a j component, and that's the first thing that we should calculate. Okay, and we should also recognize that r of t is made up of x of t times I hat plus y of t times j hat plus z of t times k hat. And that's going to help us understand what the motion is. So if we have essentially that x of t is 80 plus 2t, and y of t is negative 40, and z of t is negative 5t squared, let's see if we can try to understand what the velocity would look like. So we take the derivative of each of those functions, and this would be dx dt I hat plus dy dt. My stylus does not want to cooperate today. J hat plus dz dt k hat, which is just going to be essentially 2 I hat plus 0 minus 10t j hat. So we can interpret this as that our object has an initial velocity in the x direction of 2, and it's going to have a changing velocity in the y or j direction. In the k direction. My mistake. Okay, then we can further find the acceleration, and this is going to be just simply negative 10 k hat. Okay, so now that we have this, we can try to think about what this is describing. And by the way, a of t is just the derivative of v of t. So that means that we're going to have 3 components: dvx dt I hat, whoops, too far, dvy dt j hat, and dvz dt k hat. So what this is telling us is that we have a acceleration in the k hat direction of negative 10. We have an initial velocity in the x direction of 2. And then we have an initial position given by the coordinates 80 and negative 40. So this is basically a type of projectile. It's something that is going up in the air and going to come back down. So if I kind of set up my I hat, j hat, and k hat, we're going to see that its initial position is at 80 and negative 40. So 80 is here, negative 40 might be there. So it starts out there. And it's going to have a initial velocity in the I hat direction, okay? So it's basically going to be something like this. Okay, so we have some sort of a parabola for its motion. Okay, so now let's look at this next example. And so we have a position function that has r equals x I hat plus y j hat with these position functions t cubed minus 6 and 5t minus 3. We want to find the velocity and acceleration functions. And so v is going to be dr dt. So we'll just do this kind of quickly. So this is going to be 3t squared I hat plus 5 j hat. So what I'm doing is I'm taking dx dt, I'm taking dx dt to get vx and dy dt to get vy. From that we can get acceleration because that's going to be dv dt, and this is just going to be 6t I hat. The other components go away. So therefore, if we want the velocity and speed at 2 seconds, then we could say v of 2 is equal to, well, 2 squared is 4, so 12 I hat plus 5 j hat. Okay, or we could say that the magnitude of the speed, think Pythagorean theorem, magnitude of that speed is going to be 13 meters per second. And then the acceleration at 2 seconds is going to be 12 I hat, and that's going to be, well, probably we can write it as 12 meters per second squared I hat. Okay, so that's a pretty straightforward example. Let's try another one. Okay, so now we have a baseball outfielder throwing a long ball. We have components of position given as 30t and 10t minus 4.9t squared. We want to write vector expressions for position, velocity, and acceleration as functions of time. So we've seen this in the past couple of slides. R is going to be x I hat. We'll leave units off for now. Plus y j hat. And then we have nothing in the k hat direction. This means that velocity is going to be dr dt, which is going to be 30 I hat plus 10 minus 9.8 t j hat. So I'm doing the derivatives kind of quickly here, and I'm assuming in this video that you're comfortable enough with derivatives and power rule that you don't really need me to explain it. If you need more practice with derivatives, you should look back at the 1D motion videos that go over that in more detail. So the acceleration would just be dv dt, take another derivative, and we're just going to be left with negative 9.8 j hat. And that makes sense because we have a ball being thrown. We have an acceleration of negative 8, and that should be meters per second squared. So it's probably better if we put those units in there. Okay. And we want to write vector expressions for position, velocity, and acceleration at 2 seconds. So that's pretty easy. We just plug in r of 2. So r of 2 is going to be 60 I hat plus, that's going to be 20 minus 19.6, right? 4.9 times 4. So 20 minus 19.6 is 0.4 j hat, and then plus 0 k hat. And what this is showing is that essentially this ball will have reached kind of a height of 0 in the j hat direction. Okay, so then we plug in for v of 2, and that's going to be a constant 30 I hat, and we're going to have minus 9.6 j hat, and then a of 2 doesn't really matter, it's a constant negative 9.8, meters per second squared j hat. And of course the velocity would be meters per second and the position would be in meters. Okay, let's do one more example, and this one is a little bit more complicated. We have to be really careful about how we think about this, okay? So we're going to have an initial velocity of 4i minus 3j and a final velocity of 5i plus j. And we want to find the acceleration and then displacement during this time. Well, I think that what we can do here is think about what the acceleration would be, and the acceleration, the average acceleration would be change in velocity over change in time, and that would be v final plus a negative v initial over delta t. So you see that sometimes I use I instead of O for v initial. Okay, so this is going to be v final is going to be 5 and then minus 4 in the I hat direction, and then we're going to have 1 minus negative 3 in the j hat direction, and that's all divided by 4. So that means that our acceleration is going to be basically 1/4 I hat plus j hat. Okay, so that's the acceleration. Now we want to get the displacement during this time period, and this is a little trickier because we have to work our way backwards. Okay, so the first thing that we need to do is we need to calculate the velocity as a function of time. And basically this, whoops, too far. This velocity right here is VO, so that's when t is equal to 0, and this is v of t equal to 4. So what we can do with this is we can work backwards and we can integrate the acceleration to obtain velocity. And so this is going to be ax, that's the 1/4, and this is going to be, that 1 in front of there is going to be ay. So this means that vx is going to be the integral of ax dt, and similarly for vy. So vx is going to be 1/4 t plus a constant. But we know that from this information, when t is equal to 0, vx is actually equal to 4, because that's the x component of our initial velocity. So vx is really 1/4 t plus 4. Using a similar line of reasoning, we can get that vy is actually t minus 3. So that means that our velocity as a vector quantity is 1/4 t plus 4 I hat plus t minus 3 j hat. Okay? Now we can do one more integration to get x and y as a function of time, because x is going to be the integral of vx dt and y is going to be the integral of vy dt. Now we can assume that r is equal to 0 at t equals 0. So the constants that we get out of this integration we can toss away. Okay? So x is going to be the integral of vx here. So it's going to be essentially t squared over 8 plus 4t, and y is going to be t squared over 2 minus 3t. And if you're uncomfortable with doing integrals, you definitely want to go back and practice that, but that's basically the power rule in reverse. Okay, so finally we have an expression for r as a function of time. Okay, so r, I'm going to erase this to get a little bit more space. Okay, so r is equal to t squared over 8 plus 4t I hat plus t squared over 2 minus 3t j hat. Okay, so if I want to find out the displacement during this time period, essentially I just need to plug in 4 for t. Okay, so because delta r is going to be r final minus r initial, and we're going to say that r initial is 0, so the displacement delta r is going to be basically r of t equals 4. And that is going to be equal to 4 squared is 16 over 8 is 2, plus another 16 is 18 I hat, and then 4 squared over 2 is going to be 8, and minus 12 is going to be negative 4 j hat. So that is the final answer for this. Okay, so that's a little bit complicated, but that's how we need to set these up. And if you were like me, you might have thought that maybe you could just kind of jump and solve this pretty quickly, but you actually have to be pretty careful. Okay, so next time we're going to start talking about projectiles and how we use these r of t functions to specify projectiles.